So we're going to talk about a few things today. Focusing on floating point. We used to have half a lecture on floating point. Now we have a full lecture. And hopefully by the end of the lecture you'll understand why we're expanding that to a whole lecture. So I'll give you enough background to understand the fundamentals of floating point representation. There are a few very, very fundamental issues that most people, seem to understand but seem not to understand. So, I'll make sure that you all understand, right? And then to know the IEEE 754 floating point standard, and for CUDA and GeForce 8800, I want to make sure that you understand the speed, accuracy, precision, any deviations from the IEEE standard, the accuracy of the runtime functions, the fast math, and future performance considerations. Okay, so there are several things that you need to you need to take into consideration in order to write a piece of code that will actually work well in the future. This table is meant to be a little bit intimidating because I'm going to actually come back to this table at the end of the lecture. So what I meant to do is to highlight a few things that I want you to kind of just take a very quick look at. On the this is slide 3. So on the precision column, I want you to just kind of go through this, rounding modes, normal, actually it's enorm handling, NAND, overflow, flags, square root, division, reciprocal, log, and then there's different columns showing that what G80 does, what the x86 SSE does, what the IBM does, and Autovac, and also the cell implementation. So, for example, when we say denorm handling, G80 will do a flush to 0. SSE supports denorm, and but it takes thousands of cycles. Hopefully, by the end of the lecture, you know exactly what that means. Okay, and you will also know what the implications are. Okay, so let's go through them. And also the number of digits. For example, what does it mean by having 24 digits of accuracy? Okay, so what does that mean? So what is IEEE floating point format? This came about in the early 1980s. Okay, and what happened was back then there were lots and lots of these numerical calculators. TI has its own calculator line. HP has its own calculator line. And most of the PCs didn't even have floating point. Okay, so we're talking about 1980 or so, right? So every calculator will have a little bit different floating point behavior. So when students go to these science exams, okay, some of them are using TI, some of them are using HP. The professors started to notice something. Oftentimes, it depends on which calculator the students used. They sometimes come up with different answers. And these cause a lot of unhappiness, and the students got 0 score, and then later on found out that it was the calculator difference, and so on, okay? So, it became more and more clear that, it's kind of ridiculous to have all these calculators, right? How much can you ask for from these calculators when not any of them are produce the same result on a lot of these, calculations, right? So it gets very annoying. So there was a professor at Berkeley called Kahan. Most people call him William Kahan, but he really prefers to be called Balbo Kahan. So he started to go around the companies, and he will go around with this trench coat with all these different calculators in the trench code. So he would go to the company and he will flash and say, pick one. And then he will show you, for that calculator, which number will go wrong. Okay, because, and then he will pick up another calculator and show you exactly that other calculator will give you different answer, right? So all these companies, after a while, got the message. That is, it's just not acceptable for very simple, from most students' point of view, it shouldn't be like that, right? Whether you buy HP or you buy TI, you shouldn't get a higher score when you buy an HP calculator than a TI calculator, right? So depending on what your professor uses, right? So eventually, he led the industry effort to define a standard called IEEE 754. And this standard defined the detailed format and also the behavior of certain, situations in such a way that defined it enough that the calculations all essentially came out the same way. So, what is it? It's a floating point binary number, essentially that consists of three parts. If you look at a IEEE floating point binary number, you can divide it into three parts. Okay. The first part is S, sign. You only need one bit to distinguish between positive and negative. So it doesn't matter whether single precision, double precision, whatever, one bit. Okay, that's the sign for the whole number. The second one is exponent. This exponent gives you the order of magnitude. Okay, so whatever size of number you have, you will be scaled by 2 to the power of that exponent bit pattern. Okay, so if you have 10 bits in exponent, you can go as high as 2 to the million terms. Okay, so you have 10 bits in exponent, 2 to the 1,000, because 10 bits give you a 1,000-bit pattern, so you can have up to 2 to the 1,000th, scale. So, or you can have negative 2 to the negative 1,000. That gives you a very small representation. So this exponent bit, it really gives you the order of magnitude of that number. And then you have the mantissa. Mantissa really gives you the accuracy of your representation. How many digits of significant representation can you have depends on the number of digits you have in the mantissa. Okay? So it turns out that you can have arbitrary number of bits in your floating point representation. Most of us are used to having, let's say 32-bit single precision and 64-bit double precision. But you really can have any arbitrary number of, 5 bits, 7 bits, 9 bits, floating point, format, as long as you designate appropriate portions to the exponent, appropriate portions to the mantissa. In fact, a lot of the industry, microcontrollers, whenever they use floating point, they often use some, 16-bit floating point. Okay, so that's the reason is you don't need to have a lot of precision, but oftentimes they want to use a wide range of order of magnitude to be able to represent numbers from different order of magnitude for control purposes. Like engine controllers sometimes will use 16-bit floating point numbers. Okay, so each bit pattern, for each bit pattern, its IEEE floating point value can be evaluated based on the formula that I gave in the slide. And it's mathematics, and in this case, mathematics is justified. There are cases where people like to use math for no good reason. That's what I call a mathematization, meaning that when you don't have anything good to say, you cook up some math formulas to look like you have something good to say. But in this case, it's actually not the case. This is just a very concise expression of how you interpret those bit patterns. And so you have -1 raised to the power of s. For those of you who know that anything raised to the power of 0 is 1. Okay, so whether it's negative or positive. So it's just a simple way of saying that the number will be either -1 or +1. When you multiply by -1 or +1, so S0 you have a +1, S1 you have -1, right? So that gives you the sign. The second one is mantissa. And I'll actually talk a little bit about that because it's very important for you to understand mantissa in order to really understand floating point. And the third one is you will multiply the whole number by 2 to the exponent. And so that's what I said about the order of magnitude. But there is a restriction about IEEE floating point. Whatever mantissa you have, it has to be between 1.0 and 10.0 in binary, which means actually decimal 2. It has to be between 1 and 2 in decimal number. This is because in any scientific notation, you could have, for the same number, you can have multiple different representations. You can actually make the mantissa smaller, but raise the order of magnitude. So for example, if I don't specify any constraint on the mantissa, I can have, let's say a 0.5 decimal value to be represented in multiple ways in a binary representation. I can say it's 0.0 times 2 to the negative 2, or I can say it's 0.1 times 2 to the 0, or I can say it's 1.0 times 2 to the negative 1. By adjusting the exponent and the mantissa, by shifting the mantissa and just adjusting the exponent, I can reach the same value. Whenever you have multiple ways of representing the same number, it's problematic. Okay? Because even a very simple comparison, if you want to be able to compare two numbers and just be able to tell whether they're equal or not equal to each other, you will need to normalize their exponent and figure out how to line them up, right? Before you can do the comparison. It's just ridiculous. So what actually Foggy floating point format did was they specified that whatever mantissa you come up with has to be greater than or equal to 1 and less than 2 in the decimal sense, and it's 1, 0 in the binary sense. Okay? So that gives you a unique representation. Therefore, for the value of 0.5 decimal, you will end up with exactly one representation. The other two are going to be either too big or too small in the mantissa, so you want to disqualify. So that also specifies, exactly what each number should look like in that representation. Okay? So that's easy. Because all the mantissa values are of the form 1.xx, right? Any value between 1.0 binary and 10.0 binary should be of the form of 1 point ... right? Because it has to be less than 10.0. So it has to be 1 point ... It could be all ones, all the way, right? So that means that you don't need to represent 1, okay, in your representation, because all the mantissas will be 1 point whatever, okay? So in the spirit of being frugal, Professor Kahan is a very frugal person, as I can attest. I spent quite a few years with him, in grad school. So he has other things, but because of I'm not going to tell all the stories. So he essentially eliminated the 1 point from the representation. So all the representations, bit patterns, whatever you see, when you try to figure out what that value is, you will mentally add 1 point to the pattern, and then you can figure out the value. Okay? Why is this significant? By the way, so just a quick example. We just said that 0.5 in a 2-bit mantissa is actually 0, 0, because it's actually 1.00 times 2 to the negative 1. Okay, so for those 2 bits, we'll be representing these 2 zeros, but we're not going to represent that 1. Okay, so that should be pretty straightforward. It turns out that it's going to, unless you understand that denorm numbers don't make any sense to you. Okay, so you really need to understand it. For exponent, it turns out that if you actually go and look at the binary data, from a floating point program, sometimes the binary data doesn't seem to make sense because the bit patterns are a little bit different than you would expect. The reason is we actually don't use what we call the two's complement representation for the exponent. The exponents are actually represented with what we call the excess n representation. And for any n-bit exponent in which double precision 11 bits, single precision 8 bits. Okay? For those exponents, we will take, so n equal to 8 for single precision and 11 for double precision, right? We will use 2 to the n minus 1 as the offset, and we'll add that to the 2's complement representation of all the exponents and use that in the real representation. So for example, for actual value 0, you will expect to see 0, 0, 0, right? And that will be the 2's complement representation. But in the real implementation for a 3-bit representation, we're going to have an access 3, and that, therefore we just add 3 to the value and we'll get 0, 1, 1, and that's actually 0 in this representation. So in order to represent 2 to the 0 for the exponent, the field that you're going to see for a 3-bit exponent will be 0, 1, 1. Okay, so that's a little bit of surprise to anyone. Especially when you debug your program, you'll start to say, oh, the hardware is wrong and all that, right? No, there's nothing wrong with it. Okay. So, actual value 1, you add 3 to it, it becomes, 1, 0, 0, right? And so on. So if you systematically did it for all the positive numbers and all the negative numbers, you will end up with the numbers in the last column. And you will start to see a very interesting thing. If you start with negative 3, it's actually 0. Okay, it looks like a 0. Negative 2, it looks like a 1. Negative 1, it looks like a 2. The next big number will be 0, right? So that will be 3. And 1 will be 4, 2 will be 5, and 3 will be 6. So you shifted everything from the positive and negative numbers from 0 to the biggest number. What that does for you is that when you compare these numbers, now you can actually compare these numbers with a simple unsigned integer comparator. You can actually determine the relative relations, bigger than, smaller than, by just treating them as an unsigned integer. And that was the motivation for using these, access representations. Easier to build a hardware to do simple things. It turns out that in a 2's complement representation, you never have a truly symmetric range of representation for positive numbers and negative numbers. You always have one more bit pattern for your negative numbers. Okay, have you ever wondered about that? Because, all the binary numbers, you have even number of patterns, right? And you need to have 1, 0. So you're bound to have one more in positive or one more in negative. It turns out that for 2's complement, it's one more in negative. So this bit pattern, okay, in the access representation 1, 1, 1, which would correspond to negative 4, okay, in the 3-bit representation, is reserved so that you have a symmetric representation of positive and negative exponents. Make sense? And that pattern is used to represent infinity, not a number, and so on. So whenever you see a binary number with all 1s in the exponent, 8 1s in the single precision, 11 1s in the double precision, that means that number is either infinity or not a number, depending on the mantissa field. Okay, so that's part of the IEEE floating point standard. And so let's say we take a very simple, 5-bit hypothetical format. So if we use the spirit of IEEE floating point, what would that look like? So let's say 2-bit exponent. Okay, so that's it's 1 bit sine, 2 bits exponent, and 2 bits of mantissa. And if you go through the formula that I showed you for the access representation, the access number will be 1 in this case. So you will add 1 to all the representations. So once you add the 1, you will have essentially 0, 1, and negative 1 in terms of what you could represent with the exponent, and that will show up in the bit pattern in the third column. So if you take 0.5 and represented in our hypothetical format, it will be 1.00. Remember, I have 2 bits in the exponent, so those 2 zeros will be my exponent, okay? And then 2 to the negative 1, which is the mantissa, and then I have 2 to the minus 1. The minus 1 will be the exponent. So I look at negative 1, I see the bit pattern 0, 0 here. So I will have 0, 0 for my exponent, okay? And 0, 0 also for my mantissa, and I will have 0 for my sign, and I have a 5-bit pattern for my floating point, okay? So by this point, it should be very easy for you to figure out for any given arbitrary number of exponents you want, arbitrary number of mantissa you want, you will be able to, derive all the values that you can represent. Okay? So we're going to work through that just a little bit. I'm a little surprised that you have not asked a question yet. But I'm sure some of you are already wondering about that. And you're thinking that it's so obvious that it shouldn't be like that. But you just, you're too polite to ask that question. So, I'll just, I'll wait for you to ask that question. So it's almost like the emperor's new dress. It's so obvious that nobody's willing to ask that question. What I found out is whenever I teach this course, I always get that question from undergraduate students, but I never get that question from the grad students. And I really think that it's because it's so obvious that the grad students always just say, nah, it cannot be right. It just cannot be right. So, but the undergraduate students always ask. So let's go through the representable numbers, and it will lead into that question. So the representable numbers of any given format is the set of all the numbers that can be exactly represented in that format. Okay? So for any limited number of bits, you always have a limited number of numbers that you can represent, right? The more the bits, the more patterns you have, the more numbers you can represent. Okay? So there's no magic here. So let's say if I have an unsigned 3-bit integer format, then I can represent how many patterns? 8. 2 to the 3. What are the 8? For unsigned numbers, it will be 0 to 7. So I can draw on a number line exactly those 8 points that I can represent with that number. If I have sign, then I will go from negative 4 to positive 7, positive 3, right? So that will be the sign representation. So depending on how I interpret these bit patterns, I can shift on the number line, I can have more, I can have fewer, right? And so on. So that's easy. So that's a warm-up. So let's do the floating points. So let's take that hypothetical 5-bit again, right? So if I work out all the exponents and mantissa and signs, I will come up with all these values, right, for the 5-bit representation. That should give me 32 of those numbers, right, 5 bits. I should have 32 patterns. Each pattern will correspond to a value, right? After I calculated all this, I look at it and I say, there's something missing here. 0, right? And that was the question I was, expecting some of you to ask. In that first representation, when you assume that any number can be represented as 1 point something something, you automatically excluded 0. You could never represent 0 as 1 point something, right? Okay, now. So this is a little bit of a problem. Have you ever had a radio that you could not completely turn off the volume? Have you ever experienced that? You know what? When you turn the knob, okay, of volume towards 0, you really expect that to go completely to 0. If it still gives you a little bit of something, it really drives you crazy. I don't know your personality, but it really drives me crazy. Okay, so whenever there's you have something that you expect it to be 0, and you still hear a little bit or see a little bit. TV, same thing. When you turn off the VCR, you expect to see a black screen, right? And if something still comes up, it really drives you crazy, drives me crazy, for that matter, right? So not being able to represent a true zero in any kind of number system can be really problematic. And someone said the following, said most of the problems in engineering systems has to do with the leakage of a very small amount that eventually becomes a big problem. And whenever you have an engineering system that you cannot turn into real zero, you have this leakage going on. And that's exactly the kind of things that, a system without a zero representation will end up, because you'll be forced to represent a true zero as a very small amount. But that's not zero. So over time, you will accumulate. Over time, you will do something. And eventually, one will be crazy, right? So, that's not good. So that's what we call the no zero representation. If we follow the format just in a naive way, just did everything I said so far, you will not be able to represent zero. Most people realize this in the 1970s. If you look at the earlier computers, such as IBM, such as Digital, they all have floating point numbers. And what they did was what we call the flush to zero system, as follows. Whenever the exponent becomes zero, okay, and that's actually the smallest magnitude. Remember, we're using the excess representation, right? So whenever the exponent hits zero, that's the smallest or the most negative. In fact, it's the most negative exponent you can get in the system. Okay? Whenever it hits zero, then you treat the whole thing as zero. It doesn't matter what magnitude is. You just say, I have a zero. And that's a very easy way to detecting a zero. So this takes away several representable numbers near zero. Okay, because it depends on the number of bits you have in the mantissa. Okay? If you have a lot of bits in the mantissa, you're taking away a lot of zeros because you're taking away a lot of bit patterns. Right? So for double precision, you're taking away 2 to the whatever 23 bit patterns. So we're talking about some big number of bit patterns that we're taking away, right? So if you draw a simple line, you will actually see what the problem is. If I use my 5-bit format, okay, and then just draw the 16 positive numbers I can represent, right, with the format, and I have a symmetric negative part that I didn't show. As I approach zero, I have a phenomenon like this. For the bigger orders of magnitude, the representable numbers are farther away from each other, which is exactly what you want. I have 4 representable numbers between 2 and 4. Okay? So essentially, the gap between representable numbers is half in this region. Make sense? If I go to the next region, between 1 and 2, the representable numbers are quarter away. And this is exactly what you want. Whenever the absolute magnitude of the representable numbers are bigger, you can afford to have them a little bit farther away from each other and you don't really see the difference. Okay? Whereas when the absolute number of these representable numbers are smaller, you want them to be closer to each other so that the inaccuracies make sense. Now, what is problematic on this picture? When you move really close to zero, when the numbers are really small, suddenly you have a big gap because I just took away 4 of those values. Okay, I took 4 away of those 4 of those numbers and just flushed them to zero. Okay, they're all treated as zero now. So I have a region of numbers that tend to be, they are very small, but I will not be able to distinguish between them because the next smallest represented number beyond zero is 1. So this typically shows up in the situation where you have two, you subtracted one big number from another big number. Okay, let's say you have 10.04. Okay, 10.04 petaflops subtracted by 10 petaflops. You get 0.04. And let's say it falls into this thing. So it becomes either 0 or 1, right? And so then you say, okay, I'm going to, eventually I'm going to add another 10 to it, right? Or to multiply that by 100, let's say. Suddenly you're multiplying, one of those numbers, it became 0 or 1, and when you multiply it back, you remagnified it, okay, into a big number. And suddenly the difference that you have here will be magnified by that multiplication. And your result will look really weird. And that's the reason why these things tend to have unstable numerical, behavior. So that's why when they define the IEEE floating point representation, they look at this and say, well, all the patterns that you take away and make them into 0, 8 in this particular case, are the ones that you really, really wanted to have more accurate representation. So that's not good. So what the standard really did was what we call the D-norm numbers. Okay? And so in this method, what happened, in this particular format, what happens is that whenever the numbers get close to 0, more precisely, whenever the exponent reaches 0, then the mantissa interpretation becomes different. You actually use a different formula to calculate what the value really is. Okay? So the mantissa actually now use this formula, 0.n times 2 to the negative 2 to the power of n minus 1 to the power, right? Plus 2. And you said, who came up with that thing? And let me tell you, that thing was derived in a very, very simple way. Professor Kahan looked at the number line and said, remember there were 4 numbers that got flushed to 0 in this format, right? So he said, okay, let's pull out 3 of those numbers and make them evenly distributed between 0 and 1. And then he scratched his head a little bit and then figure out what the formula needs to be in order to get to that even distribution for any arbitrary format, right? So that's this thing, okay? So it looks intimidating, but that's really not too bad. Yes?
Is there any reason why you don't represent 0 as some mantissa pattern with the reserve exponent pattern?
Is there a reason why you don't represent, say that again.
Represent 0 as some particular mantissa pattern with the reserve exponent fit pattern. You have
yeah. That's what this is. This is because whenever that's actually what this does. Because whenever you said when exponent is 0,
exponent pattern, the one you never use, right?
I'm sorry?
The exponent pattern you never use, the one that represents the...
the ones, the all ones. Aha! Okay. The reason is this. The reason is whenever you want to have some sort of continuity. So if you mathematically, I think engineering-wise it might have worked. Okay. So whenever it gets too small, you switch to 1, 1, 1, and then you use a particular pattern for that. But in terms of, I would say detection, it becomes a little bit of a problem because whenever you see a 0 happens a lot more often than the exceptions and so on. So if you lump 0 into exceptions, then suddenly, you need to trigger a whole bunch of things with that 1, 1, 1, and that logic needs to detect 0 and all the exceptions. Whereas if you assign a unique thing to the 0, separate from the exception, then your logic design gets a little simpler. But the real reason is, mathematically, people don't like to think about it that way. Because people like to think that 0 is an extension of small numbers. So intuitively, if 0 has the biggest mantissa or something, it gets a little weird for the taste of certain people. Okay, so mathematically, people say, it's more natural this way. Now,
so implementation-wise, then, in a system that doesn't support subnormals,
yeah,
does a number that it becomes subnormal and keep everything mean?
Exactly. So what happens, with systems let me answer that question in a slightly different way, because it will be better once I finish what this means. It turns out that for all the hardware implementation, people don't like to add a piece of hardware circuitry to calculate this kind of stuff. Really what happens is that when you need to add a regular number with a denorm number, you actually need to take the denorm bit pattern and use this formula to shift the mantissa in a way that it will be compatible with the regular numbers. Remember, those two numbers have different interpretations. So you need to have a hardware circuitry to figure out exactly how to deal with the denorm number versus the regular number, so that you can always line up the floating point numbers correctly when you add them, or so on. So most people don't want to design a piece of hardware to do exactly that. So what they do is they trap in software, and they will actually trap it into software, and the software will actually line up the numbers and then do the calculation. And this goes back to the thousands of cycles that I showed in some of the tables. Whenever you actually generate a denorm number in, let's say, SSE, and you're adding a denorm number with a regular number, that addition suddenly takes thousands of cycles. Okay, because there's a piece of software that will actually go and line up the bits and do the stuff. And so, for architectures that don't want to have that kind of thing, that is, imagine in a graphics processor, okay, when suddenly when you are drawing some pictures, suddenly there's a pixel in the picture that took 1,000 times longer than others to draw. You will start to see some very weird effects. So traditionally for graphics processor, they say denorm numbers, don't worry about it. Just treat them as 0, all as zeros. Okay. So essentially, you implemented a flush to 0. They may or may not actually make all the mantissa bits into 0, but the hardware just whenever it sees a 0, the hardware just put zeros into the adder and do it. So in that sense, it doesn't matter what you actually do in terms of mantissa in the representation. They're always going to be zeros. Okay, and that's why people call it flush to 0. And the real name is actually abrupt interrupt, underflow. So whenever you can't really represent it nicely in your format, it underflows into 0 and in an abrupt way. Okay, so the nice quality of this thing is that in the smallest region, you can prove that with this formula, the distance between representable numbers is always the same as the next bigger range. Okay, this is actually just exponent value 0.00001, the next bigger exponent value. So the distance between representable points of the smallest region will be exactly the same as the next bigger range. And that at least gives you a nice quality that you are not seeing an increase in the errors. At least it maintains the magnitude of the errors. Okay. For some applications, this actually makes real difference. So what is IEEE floating-point format? This came about in the early 1980s. Okay. And what happened was, back then, there were lots and lots of these numerical calculators. TI has its own calculator line. HP has its own, calculator line. And most of the PCs didn't even have floating point. Okay? So we're talking about, 1980 or so, right? So, every calculator will have a little bit different floating point behavior. So, when students go to these science exams, okay, some of them are using TI, some of them are using HP, the professors started to notice something. Oftentimes, it depends on which calculator the students used. They sometimes come up with different answers. And these cause a lot of unhappiness, and the students got 0 score, and then later on found out that it was the calculator difference, and so on, okay? So, it became more and more clear that, it's kind of ridiculous to have all these calculators, right? How much can you ask for from these calculators when not any of them are produce the same result on a lot of these, calculations, right? So it gets very annoying. So there was a professor at Berkeley called Kahan. Most people call him William Kahan, but he really prefers to be called Belleville Kahan. So, he started to go around the companies, and he will go around with this trench coat with all these different calculators in the trench coat. So he would go to the company and he will flash and say, pick one. And then he will show you, for that calculator, which number will go wrong. Okay, because, and then he will pick up another calculator and show you exactly that other calculator will give you different answer, right? So all these companies, after a while, got the message. That is, it's just not acceptable for very simple, from most students' point of view, it shouldn't be like that, right? Whether you buy HP or you buy TI, you shouldn't get a higher score when you buy, an HP calculator than a TI calculator, right? So depending on what your professor uses, right? So eventually, he led the industry effort to define a standard called IEEE 754. And this standard defined the detailed format and also the behavior of certain, situations in such a way that defined it enough that the calculations all essentially came out the same way. So, what is it? It's a floating point binary number, essentially that consists of 3 parts. If you look at a IEEE floating point binary number, you can divide it into 3 parts. Okay. The first part is S, sign. You only need 1 bit to distinguish between positive and negative. So doesn't matter whether it's single precision, double precision, whatever, 1 bit. Okay, that's the sign for the whole number. The second one is exponent. This exponent gives you the order of magnitude. Okay, so whatever size of number you have, you will be scaled by 2 to the power of that exponent bit pattern. Okay, so if you have 10 bits in exponent, you can go as high as 2 to the million terms. Okay, so you have 10 bits in exponent, 2 to the 1,000, because 10 bits give you 1,000 bit pattern, so you can have up to 2 to the 1,000th, scale. So, or you can have negative 2 to the negative 1,000. That gives you a very small representation. So this exponent bit, it really gives you the order of magnitude of that number. And then you have the mantissa. Mantissa really gives you the accuracy of your representation. How many digits of significant representation can you have depends on the number of digits you have in the mantissa. Okay? So it turns out that you can have arbitrary number of bits in your floating point representation. Most of us are used to having, let's say 32-bit single precision and 64-bit double precision. But you really can have any arbitrary number of, 5 bits, 7 bits, 9 bits, floating point, format, as long as you designate appropriate portions to the exponent, appropriate portions to the mantissa. In fact, a lot of the industry, microcontrollers, whenever they use floating point, they often use some, 16-bit floating point. Okay, so that's the reason is you don't need to have a lot of precision, but oftentimes they want to use a wide range of order of magnitude to be able to represent numbers from different order of magnitude for control purposes. Like your engine controllers sometimes will use 16-bit floating point numbers. Okay? So each bit pattern, for each bit pattern, its IEEE floating point value can be evaluated based on the formula that I gave you in the slide. And it's mathematics. And in this case, mathematics is justified. There are cases where people like to use math for no good reason. That's what I call a mathematization, meaning that when you don't have anything good to say, you cook up some math formulas to look like you have something good to say. But in this case, it's actually not the case. This is just a very concise expression of how you interpret those bit patterns. And so you have -1 raised to the power of s. For those of you who know that anything raised to the power of 0 is 1. Okay, so whether it's negative or positive. So it's just a simple way of saying that the number will be either -1 or +1. When you multiply by -1 or +1, so S0 you have a +1, S1 you have -1, right? So that gives you the sign. The second one is mantissa. And I'll actually talk a little bit about that because it's very important for you to understand mantissa in order to really understand floating point. And the third one is you will multiply the whole number by 2 to the exponent. And so that's what I said about the order of magnitude. If you look at the instructions throughput, the integer and floating point addition, shift, min, max, floating point multiply, add, they all take 4 cycles per warp. Okay? So, but if you use integer multiply, with 32 bits, it actually takes a lot longer. And this is kind of this is the artifact from the GPU point of view. Remember, GPUs are designed to do floating point. And then you will do integer as a byproduct. If you look at the floating point, it actually has 24 bits. Okay? 23 bits represented plus that, remember that you plus the 1 bit. So in the ALU, you will have a 24-bit ALU. Okay, to do the addition and then multiplication and all that stuff. So 24-bit integers in this machine runs as fast as floating point. 32-bit integers run a lot slower than floating point in this machine. Did what I said make sense? Let me do that again. Okay, there's there's a little bit of a kind of a blank face here. When they build this machine, they say, I'm going to build a fast floating point machine. Fast floating point addition, fast floating point multiplication. If you look at the adder, it's a floating point adder. And the floating point adder would need to add the mantissa. The mantissa is really 23 bits represented in a single precision plus that one implicit bit. You need to add that implicit bit in the adder, right? 24-bit adder. So that is fast. It actually, it takes, 4 cycles for all the 32 threads in your warp to go through the adders. Now, if you want to multiply or add, 32-bit integers, suddenly you don't have enough bits in your adders and in your multipliers to produce that in a very short latency. So what happens is you actually take multiple iterations through the adder to do the first part, the second part, and to do all these swapping and so on in order to produce a bigger, the 32-bit result. And that's why it takes a lot longer. Okay? And it requires multiple cycles, and that multiple is actually not small. And you can use underscore multiply 24 or inside multiply 24 intrinsics for basically 4-cycle 24-bit integer multiply. If you know your integer number is definitely of less or equal to 24 bits in the representation, you should just use the intrinsic function, which will translate into a single multiply or add instruction. And on this machine, the guarantee is that you will get as good the speed as floating point numbers. Okay? Integer divide and modulo are very expensive. So, you know what, for the obvious cases, whenever you have a divide by 2, which 2 is a constant, the compiler will automatically translate that into shift to the right by 2, as you pointed out last time. There are a bunch of things that run reasonably fast on this machine. Reciprocal, square root, sine, cosine, log, exponent, they all take only 16 cycles per warp. Okay? And these are actually executed in hardware, special hardware function units. And you want to use underscore RCP, which is reciprocal, or underscore sine. These things will be mapped into hardware instructions. And these hardware instructions are actually executed by the SPU in one of the previous pictures. They do not give you the same number of accurate digits as the software implementation. So you will need to actually verify for your application that the hardware version is good enough in terms of accuracy. Okay, that's one of the inconveniences that you will have in order to use this. And other functions are combinations of the above. Okay, so for example, if you want to have y divided by x, there's no division directly implemented in this machine, just like the Cray machines. Seymour Cray does not like to implement division. If you want to do a division on Cray machine, you do a reciprocal and then you do a multiplication. Okay, so dividing x by y is the same as multiplying x by 1 over y, right? And the reason it's reciprocal is more easily pipelined. And therefore, you can have essentially the same pipeline structure for all these instructions, and then you just chain up the pipeline whenever you need to do the division. Square root, this is actually a kind of an interesting thing, and I never fully understood exactly. Apparently, you have to understand graphics in order to really understand this. Square root on this machine is much slower than reciprocal square root. Okay? And I think it has to do with the approximation. Whenever you use the series approximation for reciprocal square root, it seems to be a faster implementation than square root itself. When you do the series-based approximation. But I don't claim I'm an expert in that stuff. So in order to do a real square root, you actually need to take reciprocal of a square root, reciprocal square root. So that takes 32 cycles per warp. Okay? There are two types of runtime math operations. When you say underscore function, then that maps directly into hardware. Okay, so whenever you say underscore sine, that thing goes into hardware execution. But if you just say sine x, it goes into software library. However, if you use fast math flag in the compiler, it forces all the library functions that has hardware implementation into the hardware. So you can force them into the hardware. And this actually could make your code a little bit more portable, because you can use this flag to go back and forth between the hardware and the software and test it and so on, so that you can make sure that it can truly run on all generations of hardware in the future. So on the other hand, if you have some libraries that some function calls that you really know that you need a higher precision, and some of them you want to use the hardware, then you have to just use the case by case rather than forcing everything into the hardware library. So the future hardware will actually have double precision support. The chip that you're using is a single precision only. And the compiler actually, for this chip, the compiler would actually just generate all the things, all the constants, okay, into single precision for G80. Okay, so when you write a piece of CUDA code, even if you say double precision, it actually still does the single precision code generation for G80. Okay, but when you do the emulation mode, then it becomes double precision on the host. Does that make sense so far? So that's actually one of the potential pitfalls when you debug using a emulator and run the real code on the G80, because you may think that you're using double precision, and the emulator will use double precision on the CPU, so you may have tested your accuracies and you pass all the precision tests, and then when you run on the G80, everything got changed into single precision, and you may fail your accuracy test, and you may not realize that there's a discrepancy between the emulator and the hardware. Okay, so that's one of the things we always tell people. However, in this transition, if you have a careless use of double or undeclared types, you may run into more slow, the code may run into a lot slower than you expect when you switch to the next generation hardware. The reason is this. The reason is, oftentimes when you don't say anything, for example, when you use just a constant in your program, if you don't say anything, C says it's double precision. And on CPUs, that constant will become double precision constant. Any variable, even if this variable is declared as single precision, it will be converted into double precision, and then I do the multiplication on the CPU. Okay, that's just the C standard. So if you want to absolutely make sure, and you know for sure that this thing is a single precision constant, what you do is you add a little f to the end. So why can this be a little bit of a surprise? Because when you compile for G80, remember everything is forced into single precision for G80, right? So when you run on this chip, it is a single precision multiplication. But as soon as the future generation hardware takes place, the compiler is not going to force all the single precision into double precision on that chip. It's going to fall back to the C standard. So suddenly, the same statement will be run as a double precision arithmetic on that new chip. Okay? And you may start to see more of the things that got converted into double precision than you intended. And this is one of the harder to find cases unless you keep the C standard in mind. So that's why we always remind people, a couple of times through the semester, because sooner or later, many of you will be buying, or getting used to use the GPUs that have double precision, starting next year. And for your research and so on, we just don't want you to be surprised. I saw a question in the back. I answer that question? Okay. So, you know what? And also, whenever you use, you have use a standard library. Whenever you want to make sure you'll be using the single precision, let's say sine function, then you should use sine f rather than sine. And that's also the C kind of thing. Whenever you just use the sine library, implicitly you're using a double precision library. So if you really want to use single precision, you need to force it with that f in the end. Okay, we're pretty close. So this is going back to some of the questions that you just asked. Additional multiplication, in this machine has a maximal of 0.5 ULP. Okay, so what does ULP mean? Can someone tell me what ULP means?
It's written there.
What's that?
It's written there.
Yeah. Yeah, it's written there. I like the honesty. So, spelled out is called units in the least place. What does that mean? Okay. This is a fancy way of saying something very, very simple. Okay. What it really says is this. Let's go back to the to the simple example here, so that I can. When you have a particular format, you have a fixed number of mantissa bits, okay, that dictates the kind of the density of representable numbers. So whenever you have a 1 ULP, that means that whatever error you produce, you cannot go over 1. So whenever you have a number that, let's say you're supposed to generate a number, let's say somewhere here. The number that you actually generated and represented cannot be more than one representable number away from you. Okay, you cannot hop over like two numbers. And this is typically done in addition and subtraction by making sure that whatever error you produce in addition and subtraction will not generate more than one carry or lose one carry into the least significant bit of your mantissa. Okay, so that's why it's called 0.5 ULP, because what really happens in hardware is they actually, build an adder with at least one more bit position in the adder. Okay, so when you add and subtract, you will keep, at least one more bit around, and then in the end, when you generate representable numbers, you round based on that bit. So you can not generate more than half of your least representable number with that arithmetic. So that's why it's called 0.5 ULP. What that means is, in general, the error that you produce is really because in the end you cannot represent exactly the value that you just generated. So you need to round it. And during rounding, you can never generate more than half of your representable range by doing that rounding. You will always either go to this one or this one, whichever is closer, and that's always half the distance of the two representable numbers around it. So that's why it's called 0.5 ULP. That's essentially the best you can ever do in arithmetic, right? In the absolute worst case, the error you generated in the arithmetic is no more than half of the distance between two representable numbers. Okay, in that, surrounding the number that you are supposed to generate exactly. So half a ULP is really, the best you can do for most of these arithmetic operations. But sometimes you will end up generating more than that. So oftentimes, when you when you do the multiply and add, you may actually generate values that could actually be be more than that, because you are combining results. So you could generate a little bit more than that. And division in this machine can actually generate 2 ULP. And you're going to ask me, how in the world do you, would you be generating 2 ULP? And which means that whenever you generate, the result that you actually produce could be more than 4 numbers away, okay? Because 2 ULP means at least 2-bit position, so that gives you 4-bit patterns. So you could be up to 4 away from the number that you actually should have generated, okay? And the reason is, sometimes in these division algorithms, you actually do approximation, okay? And whenever the approximation is done, they need to evaluate, how much error you can produce out of the approximation. So this is no longer a rounding error. This is when you do the division, especially when you do the reciprocal, sometimes you can cut corner a little bit so that when you do the approximation for the reciprocal, you actually would introduce a little bit more error, but you can do it faster with less hardware. And then not all the rounding modes are supported in IEEE. It turns out that for those of you who are familiar with the IEEE standard, there are actually 5 rounding modes. Round to the positive infinity, round to the negative infinity, round to the close to 0, round towards the outside, and then run to the nearest without bias. So there are 5 of those modes. And this particular one only supports the run to the nearest, the nearest without bias. Denormalized numbers are not supported, as we said, right? So you just flush it to 0. So it's not denorm, and no mechanism to detect floating point exceptions. So let's go back to this table, okay? And so let's kind of go down the list a little bit. Rounding modes for floating point add and floating point multiply. in G80, it only supports round to the nearest zero and round to, nearest and round to zero. And most people actually just use round to the nearest. So that's the 0.5 ULP. Why do people want to use these other rounding modes? I always talk about this a little bit in 312. You know what? It actually has to do with how you want to lie with the data. Okay. So if you want to look good on your scientific data, you always run to the positive infinity, whenever the bigger number is. So you know what? There's a kind of a little bit of a analogy to this kind of stuff. Let's say if a bank, okay, use the floating point to represent your bank account, which is not the case, by the way. They cannot by law. But let's say if the bank does it, right? Then they will use two different rounding modes for different situations. Whenever they calculate your interest, they're going to calculate round to the zero. Whenever they calculate the interest you need to pay them, they will round to the positive infinity. And do not underestimate how much more money they can make out of this kind of business. There was a very famous case where a programmer, essentially just took the rounding error of these things, just the very small rounding error of every account and swept it into a personal account in the banking system. It took them years to catch him. And finally someone caught him in an audit, and he already got millions of dollars out of that. Okay. Small things, when they accumulate, can be very, very dangerous. Okay. They can drive you crazy, they can make people rich. Right? Okay. So, you know what? But if you look at SSE, all the four, IEEE round to near and round to nearest, depending on how you count. Sometimes we count 5. They all supposed to be all supported. And then if you look at IBM, they tend to support less. And the reason why this is happening is that when you look at G80 and Cell, these two are two comparable machines. These two machines are both designed to be highly parallel and very, very fast. So whenever you have a very highly parallel machine, you tend to have situations where you have to trade off between all the different modes and so on that you need to jam into that hardware versus how fast you want to run that hardware and take some approximations. Yes?
How do you choose between the different modes?
You actually set there is a system library API that you can use. That's right. So you can actually, I shouldn't tell you this, but for those of you who are science, physics or chemistry major, if you want your numbers to be bigger, there are ways. Okay. So the normal handling, for G80 is flush to 0, and then SSE is, was supported, but every time it actually happens, it takes thousands of cycles. Not a number, they are all supported. And remember David actually talked about this. The not a number format is actually supported in G80, right? Which color it is?
Green.
Yeah, exactly. Next time when someone from NVIDIA gives that talk, you know the answer, right? And overflow and infinity, remember that infinity, that's also one of the 111 patterns. Okay, so it actually gets supported, the overflow gets clamped into the maximum normalized number, and infinity actually also gets clamped into the max norm. And flags. So these are the flags. That means whenever you execute a piece of code, if something goes wrong in the process, okay. So let's say you're doing a matrix multiplication, you have a way to set a mode into either you vomit right away. That is, if you generate, if you generate another number for matrix multiplication, you can generate interrupt right away and terminate the program. Okay, that's called signaling. Or you can have a flat mode. That is, the hardware does not vomit. It doesn't stop execution, but you will set a flag quietly somewhere, so that in the end you will use a piece of software to detect whether that flag has been set. If the flag has been set, you can go through the data and look for other numbers and then debug your algorithm. Okay. Oftentimes for massively parallel machines, that's the way how people debug their code. Square root. it's software implementation. That is, you don't have square root instruction. You have what? Reciprocal of reciprocal root square root, right? So that's what they mean by software only. Division, same way. It's what? Exactly. Reciprocal and multiplication. And then reciprocal estimate accuracy. This thing, is about 24 bits of accuracy. And then, and reciprocal square root estimate accuracy is about 23 bits. And this is the reason why they're so proud of it. Because in their series implementation, remember they have, for division they have up to 2 ULP, right? And what that means is that, in the Mantissa, there are actually 24 bits worth, right? And so with the reciprocal and the multiplication together, in the implementation, they lost up to 2 bits of accuracy. However, in all these others, they actually lost 12 bits of accuracy in their hardware implementation. And this is the reason why David always has these 2 entries on there. They actually spend real engineering effort and real hardware to make sure. And the reason, I believe, is that in some graphics applications, the accuracy of reciprocal and reciprocal square root actually will affect the artifacts you see in the picture. I believe that's the reason, but nobody told me this. So then you have log 2 and so on. So these are all the errors that you introduce, and what they're saying here is the error that you introduce will not go beyond the 24th bit, which means that it's really accurate, right? If you think about it for a single precision implementation, it's really, really accurate.